All right, we're continuing to think about energy, and there are many, many different types of energy, but for our purposes in Physics 2201 and 2202, we focus on just four types. And we thought about one of them last time, kinetic energy, energy that an object has if it is in motion, and the total energy of a system would then be constituted by those four types of energy that we're thinking about. Kinetic energy, total kinetic energy of all the objects, all the moving objects in the system. And then these other three I'll talk about in just the next few minutes. Gravitational potential energy, elastic potential energy, and thermal energy. Now first talk about gravitational potential energy. Remember that energy is a property of a system. So in order to talk about energy at all, we have to know what is in that system that has the energy. And imagine this simple situation. I'm holding a piece of chalk and I'm raising it. For those purposes, the system will consist of the chalk and the earth. It's kind of obvious that I would want to include the chalk. Why we include the earth, that'll become clear in just a few minutes. But imagine I'm raising it at a constant velocity, and you start examining this system sometime after I've already started to move the chalk. So at the initial moment when you first start watching things, it already has some velocity. Initial velocity is not zero, and it's at some initial elevation, y initial, and you raise it through some displacement d up to the final elevation. And at that point, you don't stop, but you stop watching, but the chalk keeps on going, continues to rise beyond that point. Okay, so think for a minute about the forces acting on that piece of chalk. That's something that you always need to do as one of the early steps when you're thinking about energy. And in that case, the only two forces on the chalk are the weight of the chalk, m times g, and then a normal force from my hand pushing up on the chalk. When you think about those forces, it is essential, not optional, it's essential to distinguish between internal forces and external forces. Remember that an internal force is something that comes from a piece of the system and then acts on another piece of the system. An external force comes from outside the system, comes from some object that is not part of the system. So the weight is an internal force because it's a force. The source of this force is the earth, which is part of the system, and it's acting on the chalk, which is also part of the system, so it's an internal force. The normal force from my hand is an external force because it comes from something not in the system. My hand I did not include in the system. So why is this distinction between internal and external important? Because, as we've seen earlier, when work is done by external forces, the energy of the system can change. Work done by external forces is how a system either gains energy or has energy taken away from it. And in this case, well, the basic rule that we thought about last time is that the net work done by all the external forces is just numerically equal to the amount of energy change, right? The numerical value of the net work done by the external forces tells you exactly how much energy is either gained or lost. In this case, the net work done by external forces is going to turn out to be positive. Let's take a look at that. So our basic rule for work is this. magnitude of force, magnitude of displacement, cosine. Well, so in this case, the force is just, rather the external force is just my normal force from my hand. That's the only external force. So it is the net external force. Remember that the symbol just plain W always means the net work done by the net external force, the work done by the total of all the external forces. There's only one external force in this case. And then magnitude of the displacement, that's just the magnitude of this displacement vector d, just the distance between the initial elevation and the final elevation in this case. And then cosine theta, remember that theta is the angle between force direction and displacement direction. The force is the force from my hand pushing up, and the displacement is also up. So the force direction and the displacement direction are pointing the same way. So the difference between the force direction and the displacement direction is zero. Right? There's a 0-degree angle between their two directions. They're pointing in the same direction. So you have cosine of 0. Cosine of 0 is positive 1. So this is a magnitude, which means positive. Magnitude means positive. Magnitude is just the size or strength or absolute value. Likewise, this is a magnitude. Size, absolute value. Those are both positive numbers always. These two terms in the work equation are always positive. And so the only term in the equation that could perhaps be something other than positive is the cosine, but in this case, it's cosine of 0, which is equal to positive 1. All three terms are positive, so the work done is positive. That means the energy change is positive. In other words, this work adds energy to the system. So how does that extra energy show up? Where does that added energy show up? One thing to notice, it does not show up in additional kinetic energy, because the initial velocity and the final velocity are the same. What does that mean? Well, think about the change in kinetic energy. Change in anything is just the final value minus the initial value, and final value of kinetic energy is 1/2 mass final velocity squared minus 1/2 mass initial velocity squared. But it's been moving at a constant velocity, so the final velocity is simply the same as the initial velocity, so the final kinetic energy is just the same as the initial kinetic energy. These two terms are the same size, so they cancel out. They add up to 0. In other words, the kinetic energy has not changed. The additional energy put into the system did not show up as additional kinetic energy. Nothing was added to the kinetic energy. But that energy had to go somewhere, and where it goes, if it doesn't go into kinetic energy, it's going to go into either thermal energy or some kind of potential energy. And it only goes into thermal energy under certain circumstances that we'll think about in a minute. And those circumstances don't apply in this case, as we'll think about in a minute, so it must have gone into potential energy, specifically gravitational potential energy. Let's think in a little bit more detail about the work done on the chalk and where that energy goes. Go back to our equation for work. work done was equal to the magnitude of the force, the normal force from my hand on the chalk, times the size of the displacement, and then cosine of 0, which was just plain 1. But now, remember the chalk was moving at a constant velocity, and the forces on the chalk were the normal force and the weight, but constant velocity means 0 acceleration, no change in velocity. And Newton's second law tells us if there is no acceleration, that has to be because there is no net force. Net force is just plain 0. But of course, the net force is just the combination of this upward force and this downward force. And if they combine to give you 0, that's because these two forces are canceling out, which means they have to have the same strength in order to cancel each other out. So the normal force from my hand on the chalk is just equal to the weight of the chalk. So this term, the magnitude of the normal force, is just equal to the magnitude of the chalk's weight. So I could write this as mg. So I'll do that. Now, for the displacement term, displacement in this case is just the difference between the final elevation and the initial elevation. Right, if I just imagine a coordinate system where the positive direction is up, then this final elevation coordinate is a bigger number than, this final elevation number is a bigger number than the initial elevation. So the size of the displacement, the distance between here and here, is just final elevation minus initial elevation. That's just equal to the magnitude of the displacement vector. Now, let me do the distributive property on these numbers. So the work done is in this case equal to mg final elevation minus mg initial elevation, and that looks like a change in something because it's a final something minus an initial something, and that something is what we call gravitational potential energy. And our rule for calculating a gravitational potential energy looks just like this. Gravitational potential energy is mass times g times whatever the elevation is. So this is just final minus initial gravitational potential energy. The work done is just final minus initial gravitational potential energy. We will always use the capital U to indicate some kind of potential energy. And there are different kinds of potential energy, so we'll use subscripts to distinguish one kind of potential energy from another. So U for potential energy, G for gravitational potential energy. Or to put this in the shortest, most concise way, the work done is just change in gravitational potential energy. The work done was positive, so change in gravitational potential energy is positive. The change in gravitational potential energy was an increase. When work was done on the system, energy was not added to the kinetic energy, but it was added to the gravitational potential energy. One other thing about potential energies. Potential energies always happen because there's some kind of a force, which is an interaction between two different things. In this case, the force is gravity, and the two different things interacting by gravity are the chalk and the earth. Because of that, we always say that potential energy is something that is shared between those two things that are interacting via the force. So the two things that are interacting via gravitational force, chalk and earth, share the gravitational potential energy. So in order to talk in a consistent way about potential energy, we have to include both of those things in the system. Both of the things that share the gravitational potential energy. And that'll be true for other kinds of potential energy that we see. Elastic potential energy that we'll look at in just a minute, and then in 2202 there will be electrical potential energy. So now let's think about elastic potential energy. So now we've got this, our rule for calculating kinetic energy. Now we also have a rule for calculating gravitational potential energy. Mg times elevation. Now, elastic potential energy. And imagine now a spring. One end is attached to a wall so it doesn't move. And then when a spring is not stretched and not squeezed, not compressed, the right end of the spring ends here. And we'll set up a coordinate system where we call that x equal to 0, and then the positive direction to the right and negative direction to the left. Now, imagine that we stretch the spring. Stretch the spring this far. When we stretch or squeeze the spring, we always talk about displacements. Displacement meaning how far you have moved this part of the spring, the part of the spring that you're actually pulling or pushing on, how far you have moved it away from its normal resting position. So there is a displacement this way. And being an elastic object, the spring will try to snap back to its original shorter length. So if you're holding onto it here, as you pull it farther, it's trying to snap back this way, which means the spring, as it tries to snap back to its original shorter length, is going to be pulling to the left on your hand. That pull happens because the spring is being stretched, and that pull on your hand is what we often call just a spring force. The spring force points that way, opposite to the displacement. It's trying to pull the spring back to its original shape. In other words, it's pulling opposite to the displacement. We have a rule for calculating the size of a spring force. The size of a spring force is just proportional to the size of the displacement. K is what we call the proportionality constant here. And we put this minus sign here to indicate that the spring force points opposite to the displacement. Right? In this case, the spring was stretched in the positive direction, so this is positive, and therefore the spring force pulls in the negative direction. Same kind of thing might happen if you squeeze the spring, compress it, push it to the right instead of pulling it to the left. So in that case, the spring is compressed like this, so the end that you've been touching, the end that you've been moving, has a displacement like that, a displacement to the left. And of course, again, being elastic, when you push the spring this way, it's going to try to snap back to its original longer length. And as it tries to snap back, it's going to push on your hand, push to the right. And that push, which is there because the spring is trying to restore itself to its original shape, that push is now the spring force. And it's a force to the right. And once again, just like in this case, we see that the displacement points to the left, the spring force points to the right. Displacement and force point in opposite directions. That's always the way the spring force works. Springs themselves aren't terribly interesting things, but they're useful because they are a simple model that tells us a lot about any kind of elastic system, the behavior of any system that's been distorted in some way, stretched, squeezed, bent, twisted, whatever, and is trying to return to its original shape. There are a lot of situations like that, other than just springs. But springs are a nice model that helps us to understand all elastic systems. Now, when I pulled on the spring and when I pushed on the spring, I was doing work on that spring. Again, I was doing work. And so I gave energy to the system. Where does that energy show up? Well, let's look at one specific example. Let's look at the example where I pull on the spring. So the initial state, the spring looks like that. The right end of the spring is at x equals 0. And then I pull on the spring, so my force is a pull to the right, and as a result, the end of the spring has a displacement to the right. So, remember, work done is the strength of the force times distance times cosine of the angle between the force and the displacement. Now, one tricky thing here, this force here is a force from me on the spring. As the spring gets stretched more and more, the spring pulls back harder and harder, right? Bigger displacement means the spring pulls back with a stronger spring force. So I have to pull harder and harder to keep the spring moving to the right. So this force is not constant, it's increasing. But let's say that, just to keep things simple, I'm say it's increasing at a constant rate so that we could actually talk reasonably about an average force over the whole stretching time. That's the way the book asks you to think about it. Now, initially, in the initial state, the right-hand end of the spring is not moving, so it has a velocity of 0. And of course, when I have finished stretching the spring, again, I've stopped moving the right-hand end of the spring. So again, the velocity of that right-hand end of the spring is 0. I've given energy to the spring, but that energy does not show up as additional kinetic energy because in the final state, nothing is moving, so there is no kinetic energy. And in the initial state, nothing was moving, so there was no kinetic energy. Or to say that algebraically, initial kinetic energy, 1/2 mass, initial velocity squared, which is just 1/2 mass, 0 meters per second, and then the final kinetic energy is 1/2 mass final velocity squared, in other words 1/2 mass, 0 meters per second. So the change in kinetic energy, which is just final minus initial, is in the final state 0 kinetic energy minus 0 in the initial state. There, when I did work and gave energy to the system, none of that energy that I gave showed up as additional kinetic energy. It must have shown up somewhere else, and it shows up as another kind of potential energy. By the way, I know for sure that the work I did gave energy rather than took away energy, because this work is positive. Right? That's a magnitude, so it must be positive. That's a magnitude, so it must be positive. And in this case, cosine of theta, just like in the previous example, that angle, the angle between the force direction and the displacement direction, well, is again 0, because the force that I'm applying to the spring points to the left, and the displacement, the direction of the spring's motion, is to the left. So the angle between force direction and displacement direction is no angle at all, 0 degrees, and again, cosine of 0 is positive 1. So again, just like in the example with the chalk, I do positive work on this system and give energy to this system. But the energy I give doesn't show up as any increased kinetic energy. The kinetic energy started out as 0 and ends up as 0. So where did it go? It went into additional potential energy, and as is stated in the book, the rule for calculating how much potential energy a stretched or squeezed system has looks like this. Elastic potential energy, 1/2 K, or K is that same K factor that appeared in the rule for spring force, times displacement squared. So whatever number this is, however far away from the normal resting undisturbed state, however far I pull the spring, that is the displacement that goes right here. And notice that as I pull farther and farther, the elastic potential energy increases faster and faster. Because let's say I pull it a certain length and then let it snap back to its original shape, and then pull on it twice as far. So the second time I pull on it, the displacement is twice as big as it was in the first case. But looking at this rule, the elastic potential energy doesn't depend on the displacement, it depends on the displacement squared. So how does the displacement squared change? Well, the displacement squared is just the square of this, which is equal to the square of this. So that variable that we call displacement squared original displacement squared. Displacement squared is 4 times larger if I pull twice as far. In other words, if I double the displacement, I don't double the energy, I quadruple the elastic potential energy. All right, so that's we have nice equations for 3 of our 4 types of energy. We don't have a nice equation for thermal energy. That's okay. We'll be able to get along without an equation. Now let's look at an example of how we use all this stuff to analyze an energy type situation. So here's our example. Before that, let me remind everybody the net work done by the net external force on a system is what changes the energy of a system, and the energy and the change in the total energy could come from one or more changes in the different types of energy. A change in kinetic energy could contribute to the total energy change, and there may be a gravitational potential energy change, there may be elastic potential energy change, and there may be thermal energy change. We'll look at a specific example here. Let's say there's a firefighter on the 2nd floor of the firehouse, and old-fashioned firehouse with a pole to slide down, and the firefighter does that, slides down a distance of let's see, what did I call here? 10 meters from the 2nd floor down to the ground floor. And when the firefighter first steps onto the pole, the firefighter starts to speed up while falling, while sliding down the pole, but starts from essentially 0 velocity up at this initial elevation, and then falls, and when it gets to the ground floor, an instant before the firefighter hits the ground floor and stops, the velocity was, let's say, 2 meters per second. Now it turns out that if the firefighter had been in free fall and had fallen 10 meters, the velocity here would be much, much bigger than just 2 meters per second. What kept the firefighter from getting such a high speed, dangerously high speed, land too fast, and in order to stop something moving that fast, the floor would have to apply a really strong force on the firefighter, and the firefighter would get injured. But what keeps the firefighter from accelerating too much downward is an upward force, friction from the pole. And one important point here is, as mentioned in the book, and it's a key idea, whenever there is friction, thermal energy is gained. The work done by friction on something is always negative work, as I pointed out in the previous week's video. Right? The value of work done by a friction force is always a negative number. So negative work means energy taken away from the thing that's having work done on it. Where does that energy go when it's taken away? Well, if it's taken away by work done by friction, it goes into thermal energy. So there's negative work done by friction force. It's kinetic friction because the firefighter is sliding, and so feeling a kinetic friction force opposite to the direction of the slide. There's energy taken away from the firefighter, energy that would have shown up as kinetic energy otherwise, but instead of showing up as a huge amount of kinetic energy, it's taken away from the firefighter, never becomes kinetic energy, the firefighter, and goes into thermal energy instead. Remember what thermal energy is. It's just the total kinetic plus potential energy of all the molecules that constitute all the objects in the system. And if you increase the thermal energy, you can detect an increase in thermal energy by noticing an increase in temperature. Basically, what temperature really is the thing that we can measure, which will tell us what's going on with the total kinetic plus potential energy of all the molecules. We can't measure individually the kinetic energy of each molecule or the potential energy of each molecule, but we have thermal energy that tells us what the total energy of all the molecules is like. Anyway, what we're wondering about here is how much energy gets taken away by the work that friction does. How much energy, in other words, is given to the thermal energy, or what is the increase in thermal energy in this case when the firefighter slides down from the second floor to the first floor? That is the question. That's the question we're trying to answer. And how do we approach that kind of a question from an energy point of view? Well, like I said back at the beginning, energy is a property of a system, so the first thing is to decide what must go into a system. And I've written out 4 simple rules. They're also in the textbook. 4 simple rules for deciding what ought to go into a system. That's a file in the Chapter 10 folder. So look at that. Follow those rules. Using those rules to decide what goes into a system is always the first step in any energy problem. So in this case, what goes into the system? First rule tells us that anything that is moving and therefore has kinetic energy ought to go into the system. So the firefighter is moving. And second rule tells us that if that movement involves a change in elevation, that means there's a change in gravitational potential energy. Remember, gravitational potential energy, mass g elevation, for any one particular thing, and watching it move, it's the same thing, so mass doesn't change. So gravitational potential energy is directly proportional to elevation. In this case, the firefighter's elevation was decreasing, so there was a decrease in the elevation, therefore a decrease in gravitational potential energy. If there is any change in gravitational potential energy because of a change in elevation, then you have to pay attention to gravitational potential energy, and therefore you have to include in the system all of the things that share that gravitational potential energy. And just like in the chalk example, the things that share the gravitational potential energy are the moving thing, the firefighter in this case, and the earth. The third rule tells us that any elastic object that's being stretched or bent or squeezed or twisted, distorted in any way, is going to gain some elastic potential energy when it has work done on it, the work that does the twisting and the stretching or the squeezing. So that elastic object has to be included in the system. there are no such elastic objects in this system, so nothing to worry about there. Last rule is that whenever there is friction, and there is friction in this case, any object that is the source of a friction force or feels a friction force, any object involved in a friction force must be included in the system. And in this case, there's a friction force coming on the firefighter. That force comes from the pole, so we have to include the pole in the system. All right, now, what are the consequences of choosing a system this way? Well, to answer that, we first have to answer a very common question, a question that you really should ask every single time you've got almost any physics situation. What forces are at work here? And in this case, the forces are just the firefighter's weight, and then while the firefighter is sliding down, there's a kinetic friction force. Kinetic friction always points opposite to the direction of motion, so the kinetic friction force is up, like that. Now, when we're talking about energy, we're talking about a property of a system, and we need to know what's in the system and what's out of the system. Now, these are the objects that are in the system. We also need to know about what forces are in the system and what forces are coming from outside the system, internal versus external forces. Weight is an internal force because it comes from the Earth, and Earth is part of the system. Kinetic friction is an internal force also because it comes from the pole, which is part of the system, and acts on the firefighter, who is part of the system. Now here's the important consequence of all that. In this case, because of the way we defined the system, all the forces turn out to be internal forces. And when all the forces are internal forces, of course, that means there is no such thing as an external force in this case. There are no external forces in this case. So, obviously, the work done, the net work done by all the external forces has to be zero, because there are no external forces. The work done by all the external forces is zero, which means there is no change in the system's energy. The system's energy stays constant, or the system's energy is conserved. Constant, conserved, whatever word you want to choose, they mean the same thing. So there's no change in the total energy, but there are changes in the individual types of energy, and we need to be aware of what they are in order to get everything correct here. There is, for example, an increase in kinetic energy. The change in kinetic energy is positive because the initial velocity of the firefighter is zero and the final velocity of the firefighter is greater than zero. So the initial kinetic energy was zero and the final kinetic energy is greater than zero. Gravitational potential energy has a negative change, a decrease, because elevation decreased. And gravitational potential energy is directly proportional to elevation, so when this variable decreases, the directly proportional variable, gravitational potential energy, must decrease. A negative change. Nothing happens to elastic potential energy. Throughout this whole process, there is no elastic potential energy at all because there are no elastic objects being squeezed or stretched. But there's friction, and whenever friction happens, energy is added to thermal energy. So in other words, there's a transformation of some kinds of energy into other kinds of energy. We will have a lot of gravitational potential energy at the start, but then that gravitational potential energy decreases, and where does that energy go? Some of it goes into kinetic energy, and a lot of it will go into thermal energy. So now let's do the numbers and find out how much actually goes into thermal energy. And the way we do the numbers, I always refer to that as writing out this equation in detail, writing out the energy change equation in detail. Whenever you see those words, writing out the energy equation in detail, what you will do will be something like the following. We know that the grand total change in the total energy of the system was 0, so we'll call it 0 instead of delta E. We know there was a change in the kinetic energy. Kinetic energy increased, so there is a difference between 1/2 mass final velocity squared minus 1/2 mass initial velocity squared. The final and initial velocities are different, so the final and initial kinetic energies are different. And we know there was a change in gravitational potential energy, and the change is, as always, final minus initial, final potential energy, mg times final elevation, minus initial potential energy, mg initial potential energy. And then there was no change at all here, so that doesn't add anything to our equation. And then this change was a negative change, a decrease. And then this changes also. This is a positive number, this is not 0, and since this is not 0, we include it in the equation. We don't have an equation for change in thermal energy, but so we'll just call it change in thermal energy. And now we know enough numbers to insert numbers into this equation so that when we're finished putting in numbers, the only unknown is thermal energy, and we can solve the equation for thermal energy. Simplify just a little bit. Initially, remember, the firefighters started with 0 velocity. Initial velocity is 0, so this whole term here, the initial kinetic energy, is 0, because the initial velocity was 0. And then the actual numerical values for final and initial elevation depend on how you set up the coordinate system. You're free to set it up any way you like, as is described in the book, because the only thing that matters is the difference between initial and final potential energy, and that difference is going to be the same no matter how you set up the coordinate system. It's easiest to put the 0 level of elevation at either the start or the finish. So the final elevation is down here, and since this is the lower elevation, we'll call that the 0. We'll call that elevation 0. And then put the positive direction up and the negative direction down. So the second floor, remember, was 10 meters above the ground floor. So y initial, the initial elevation, is plus 10 meters. So that means final elevation is 0. That number is 0, so the final gravitational potential energy is 0. All right. Two terms disappear from the written out in detail version of the energy change equation. And all we have left is this minus this plus this, all equal to 0. Now let's put in the numbers. Zero equals 1/2 mass. Let's say the firefighter's mass is 80 kilograms. Final velocity was 2.0 meters per second, and that's squared. Then this, the initial gravitational potential energy, which is mass, times g, 9.8 meters per second squared. Don't ever write minus 9.8. The minus, no. G, the symbol G, means the magnitude of the gravitational acceleration. So nothing to do with direction. The magnitude is just plain 9.8 meters per second times the elevation, which was 10 meters. Plus thermal energy change. Okay, so when you do all that, the number you finally come up with is not a large number, just 160 joules. Joules is our normal unit for energy, and if all of your lengths are in meters, which means all of your velocities are in meters per second, and if all of your masses are in kilograms, then the energy number that you get is automatically in joules. And then this would be minus a big number, 7,840 joules, plus change in the thermal energy. So, and all of that is equal to 0. So when you do when you solve this equation here for the change in thermal energy, the change in thermal energy comes out to so 7,680 joules. In other words, in this system, initially, there were 7,840 joules of gravitational potential energy that disappeared because 160 joules of that went into kinetic energy of the firefighter, and 7,680 joules went into the thermal energy. In other words, way more than 90%, way more than 95% of the energy that the system started with ends up just in thermal energy. And that's a good thing, because you don't want to give the firefighter too much kinetic energy, because if you did, the firefighter would be going too fast when they landed, and they'd get injured. Okay, this might seem like a long process, partly because I went very slowly through it, but with practice, it'll get shorter, and you could either try at this point the lecture exercises, or look at the second part 2 of all this of the energy video, and then try the lecture exercise after part 2. There's some other stuff in the part 2 of the video that that you will need to see. There's some other assignments coming up that you cannot do until you have finished the both parts of the video. But you can try the lecture exercise at least if you feel like it at this moment.